So my name is Matt, and I'm going to be talking about how you or anyone could build a bank in Go, which sounds a bit ridiculous. But brief introduction first. So my name is Matt. I'm on Twitter here, or various other places on the internet. And I'm primarily a back-end engineer. I do a bit of everything. You kind of have to in small startups, as I'm sure everyone knows. And at the moment, I'm working for a company called Mondo. And we're actually building a bank, a completely new bank from scratch. And we're currently in the extremely long application process for a full UK banking license. And that's quite cool, because that means you get all the standard guarantees that any other retail bank in the UK gives you. Things like 85 grand of your money is safe until, I think, some point next year when it's 75 grand of your money will be safe, regardless of where you put it and regardless if the bank fails. And there's a lot of companies that are kind of bringing out all sorts of new financial products. There's a lot of kind of disaggregation that's happening in the market. But fundamentally, we're a bank, or at least we will be at some point next year. However, for me, I don't know if this is the same for everyone, banking feels a bit like this. So this is like 1800s, there's branches, you have to go there. Now you can ring people up, that's great. Internet banking is not really a thing. And kind of at the core of most existing banks is this ridiculous kind of archaic monolithic systems that quite literally still run code from the 1960s. This is an IBM 360. For anyone who wrote code that ran on IBM 360, you can actually buy a Z series and it will still run your code. Like, you can run code that's 50 years old, which, I mean, is kind of mind-blowing that IBM has done that. That's incredible. But if you want to move fast as a business, that's a little bit of a constraint, especially if you wrote loads and loads of COBOL in the 70s, which a lot of banking systems still run on, where everyone who knows COBOL has now retired, or they come back and they charge incredible fees. I kind of wish I knew COBOL, to be honest. However, the world has kind of moved on a bit, so everyone uses their mobile now, and we kind of expect real-time banking on your phone. And that doesn't really happen for me. I've tried pretty much every high street bank and a lot of kind of other alternatives, and it's still kind of lacking a bit. And I'm not the only person who thinks that, so you can literally go on Twitter and you can search for horror stories from literally any high street bank. They're just kind of appalling UX and systems that just aren't really kind of set to work in 2015. But I mean, that's an easy target to bash. So what could we do if we started from scratch? If we literally started with no code at all, and we could build something that was completely fresh, take it in any direction we want. And that's what we're doing at Mondo. So we're mobile first, which is quite cool, because then you can literally build just the things you want and rapidly iterate on that product. So things like, I don't know, being able to search in your app for coffee and see how much you spent on coffee. You could actually search just this week, and that's all freeform text. You could get graphs of things you're doing, see everything that you bought. You get real-time push notifications. You could look at your card. You could, I don't know, press a button in your app and pause your card, so now it declines. That'd be quite useful. And then maybe you could unpause it. That'd also be pretty cool. So you just turn it back on, which at the moment, anytime I lose my card, even if I think it's there, I have to ring up my bank and then wait 5 to 10 days to get a replacement. This is a database flag, right? There's a bool somewhere that defines whether a card works or doesn't work. And all your bank has to do is set that to false, and then when they get an authorization message, say, it's blocked. Just don't honor that. But no one can do that, apparently. So if you're building things from scratch, you really could. And you could build more contextual things as well. So for example, I get real-time push notifications every time I shop at Itsu and buy some sushi. But you'll notice that is a sushi there. It's a sushi. This is really easy. Anyone who's built web applications, you can look up the merchant. It's Itsu. You probably bought sushi. let's put a sushi emoji in. That's super easy. And support things like non-ASCII characters. Like, everyone here has sent a BACS transfer, right? Like, you've sent money to someone else. And it's crazy archaic, and it takes 3 days. And now we have faster payments. Yes, real time, kind of. Except in Europe, they have SEPA, and it launched in 2008, and it doesn't support these characters. Like, who designed this? So you send that through, and you lose the meaning of that. That's a different word. So anyone who likes Monty Python, kind of reference there. Or if you're, say, in Turkey, then you have eyes without dots. And if you sent that through SEPA, you'd get eyes with dots. And in this particular case, if you Google that word, that went in through the text message system as an SMS, and adding those dots caused like 2 people to die and 3 people to go to prison, like just to a complete misunderstanding in a very heated exchange, literally caused people to die. And obviously emojis, like that is never going to happen. So if we were starting from scratch, building a standard web application, where would we start? We'd normally have an application and a database. And over time, we'd kind of add lots of features, our application get really big, and this kind of applies in any language. So, I don't know, I used to do a lot of PHP a long time ago, in the dark ages. Or if you're building like a huge Rails app, for example, like these things get progressively more complicated as you build additional features. And as you're scaling a company, you're going to be adding lots of extra features because you need to like move with the market and really kind of add the things that your customer want. You need to react to change very quickly. So your application will get bigger. And then you'll have to scale out a bit, so you maybe have some databases. But that's not the only thing that you're going to do. You're going to add like lots of extra things, maybe some searching, caching to make things a bit faster, all sorts of extra features that your customers need. And eventually you have this like crazy, crazy monolith, which everyone has to look at. And every time you want to make a change, you need to coordinate with everyone in your team. And I don't know, there's like, 100 people here, 80 people. Like, imagine if everyone here were the people you worked with on a large development team, and you had to somehow coordinate one application being deployed across all of you. That'd be terrifying. And that's not something that anyone wants to deal with. So this is something that's become like very popular over the last few years. Large companies who've scaled both their application to a huge number of users, but also have scaled their like development team so that they can move much faster, have like these huge monoliths that have slowed their progress, and they can't develop things as fast as they need to. We've started to see a lot of people kind of breaking these things down, pulling stuff out into separate applications. You get service-oriented architectures, and we can like break our whole application apart into lots of small pieces. And these are all communicating in some fashion. And if I'm working on a particular section of the application, I don't need to know how other sections work. And that's great if you have a development team of 10, 50, 500. That scales. So you can build your company much, much quicker. However, for each one of these things, you need to like make sure that they're built in the correct way. So single responsibility principle is a good process to follow, where you're ensuring that you have an application and it does one thing, but it does it extremely well. And if you need that to scale, you can scale it potentially horizontally, or some applications will scale better vertically. But you can deal with that scaling actually just in that one application, and everything else doesn't need to know about that. You've reduced the complexity. And in order to do that, you need a bounded context. So within your business, you would take one particular aspect, that might be storing customer data, or storing a very specific section of customer data. And this application will be responsible just for that. And of course, if you're doing that, you need extremely well-defined interfaces around the edges of these applications, so that if I need to get some data from someone else, I have an interface, and I don't need to know how it works behind that. So people can change the complete implementation behind the scenes, and I'm unaware. I'm just a customer of an interface. And doing all of this allows you to then like compose applications out of a whole series of services. So, for example, if you if you've already built a service that sends text messages and scales incredibly and is extremely quick and does all those things, if I need to like write a particular thing to send text messages, all I have to do is make an API call, and someone else can deal with that. And we already have this. Things like if you're sending emails, you're probably going to be using something like MailChimp or Mandrill or SendGrid or something like that, maybe Twilio for text messages. Like, there are services that then allow you to actually just replace chunks of your infrastructure with third-party services. So if we started right from the beginning, we'd probably have a load balancer, and then we'd have some HTTP API. I don't know, if you're building an app, you're probably dealing with like JSON over HTTP. In our case, we would have that as a routing layer that allows us to route things. And then we'd route that through some form of transport. That could be HTTP, it could be AMQP, like RabbitMQ, some other message bus, and we'd route that into a service. And in fact, we'd have lots of these services. And crucially, each one of those would have its own database, if it was storing data. We shouldn't ever be sharing databases using like shared access between these applications, because otherwise we're going to like have some code here and some code here, and we'll have a database that has a particular domain model, and we'll change the code there, and we'll definitely forget about that code, and then everything will break. And then we can wrap this, so if we're deploying across multiple data centers, so if you're running on Amazon, you'd probably be deploying across multiple availability zones, or potentially multiple regions, and we can just scale this out essentially horizontally across a number of data centers. Obviously, at this point, you have like consistency issues. So, I mean, at Mondo, we use a lot of Cassandra, which lets us have like eventually consistent data. But it also means that we can survive like machines failing. We can spread across multiple data centers, and we let some well-tested database deal with the kind of replication across those things. However, how does Go fit into this? So in our case, we had the opportunity to start from scratch. We could have picked anything. We could have built a bank in any language whatsoever with any tooling. Why did we pick Go? So to start with, it's statically typed. So if you're dealing with money, I would recommend not using floating point numbers, just in case. You don't want someone's balance to be off, and you certainly don't want that number to be able to be converted between a float and an integer. Like, it's quite important that doesn't happen. I'd say that's probably the most important thing. You definitely don't want that to happen in your core banking systems. But beyond that, Go has incredible, like, kind of first-class concurrency. So it has Go routines, which are essentially lightweight threads, and channels, which are a way of communicating between these. And the whole mantra is to communicate via things like channels rather than by sharing memory and having like mutexes where you're like acquiring a read lock on that section of memory, modifying it, and then unlocking it. And that's quite good because it allows you to write highly concurrent code that can scale really, really well. And potentially you have like applications with hundreds of thousands of Go routines running at the same time with sub-millisecond latency. On top of that, the networking like stuff that comes in the standard library. So the standard library in Go is really, really good. And it provides all of the basics that you need for applications. And the networking in particular is really good. So really good networking support. HTTP2 has just been merged into the tip, so it's now standard in the language. And that means if you actually created a HTTP server, if you now download the latest version of Go, it will seamlessly upgrade to HTTP2. Like, that's just in the language. You don't need to even think about it. And it's very easy to do things like network pooling, connection pooling, and things like that. And deployability, for me, is the most important one. When you compile something in Go, you get a single file, like one binary that is executable. And you can put that anywhere. You don't need to have, like, the JVM installed, and then you put your code, like, put your WAR file or something in a Tomcat servlet. You don't have to do any of that. You just take a binary, you put it on any box that has the same architecture that you compiled it against, and you just execute it, and that's it. And for me, that's incredible because I don't have to deal with shipping like huge blocks of files around or like making sure I have all the right versions of libraries. I can just have a box, and I put this binary there, and I execute it, and maybe I run 1,000 of those, and it's all fine. So if you're starting with a microservice architecture in Go, there's a few options. We can get some libraries. So gRPC has come out of, I think, Stripe and Google, which is quite a nice way of communicating between these services. GoKit has lots of library support. Kite's another one, and Go Micro is another one. So these are all like basically fairly low-level frameworks that you can just use to build services, and they will communicate amongst themselves. In our case, actually, none of these things existed in February, which is a little bit annoying. So we have our own, which are open source and MIT licensed. So these are on GitHub. And essentially, we have a transport layer, and then Mercury, which is our client-server library. So Mercury allows us to very quickly build a new service with a known API, and then we can get a client that can talk to it. And it will deal with all the transport details, and it allows us to build things very, very, very quickly, to the point that I should be able to ship a new feature within a couple of hours, which obviously for a bank is kind of unheard of. And that's something that we genuinely do. We had, when I used to work at Halo, we had a very similar infrastructure, and we would legitimately ship features the same day that we started writing them, and then we just iterate on that. So to go back to our example with a load balancer and some HTTP API, what we're actually doing is we have this as just a routing layer. So we take our HTTP request, we marshal it, but we want to be able to rapidly add new features and new sections of our API. So it'd be quite nice if the thing that's terminating the HTTP connections was very stable. So in fact, all we do is that takes in a HTTP request and then sends it on to another service that is that section of the API. So we have lots of these. And if I want to set, add a new feature that is some API / thing, I can just deploy it, and I'll just get that extra path section in our API. And that means also if I'm deploying one, I can only break a small section of our API, which is quite nice, which will probably happen at some point. But definitely not in production, because obviously your bank has to be super reliable, and we'll come on to that in a little bit. And then behind this, we're going to coordinate with some services. So these are going to do specific things within our infrastructure. They might be loading customer data, sending text messages, applying transactions to your account, those kind of things. And they'll be backed by a database maybe, or some other database, or maybe external providers. So if you're sending text messages, you'll probably have some nice thing within your infrastructure which does things like rate limiting and passing on text messages to Twilio or something like that. And eventually this thing will grow. And we'll add more and more services, and our whole development team don't need to know about how these things work. We obviously coordinate between teams. And eventually we'll end up with some crazy infrastructure that no one quite will understand, but in theory works very well. And there's a problem with complexity there, which we'll have to chat about. But what are these boxes? So in our case, when I talk about a service, I'm talking specifically about three things. Some form of handler that is going to do an action. There's a huge number of comparisons across frameworks. And then in our case, we're using this Mercury library, which provides those and allows us to register multiple handlers within a given service. And then we have some logic, which will be executed as a result of that. And then we've probably got storage as well. And in our case, we also have libraries that abstract these. So things like Cassandra, Postgres, queuing systems, stuff like that. And these are quite useful because if you're writing a framework that is intended to make developers at your company more productive, you can do lots of really cool things. If I'm writing to Cassandra, if I have a Cassandra cluster of 6 nodes, I only need to write to one of them, but I need to find the IP addresses of these things. And it'd be really cool if I didn't have to worry about that. I could just write some logic, and I knew that if I imported our Cassandra library, it would automatically configure itself, deal with the fact I need to be writing at a particular quorum, and find the right nodes, and automatically connect to new ones, deal with connection pooling. All of that stuff should be handled for me. And in a lot of cases, those things are, connection pooling, your client will definitely do that. But finding the right IP addresses and reconnecting if they change, probably not. So by abstracting that, we can like pull in config dynamically. We can do things like fast reloads, where we maybe get a notification configuration has changed, particularly if you're using auto-scaling groups in Amazon. You can use like SNS notifications to get notifications of when nodes go up and down. You could use health checks on these things to change when the configuration, what's in the configuration. And then your library could just automatically adjust. Meanwhile, all you have to focus on is the core business logic. So you can ship these things much, much quicker. And in Go, we start with a main function. So every program starts with this. Func main, some code, done. And in our services using this Mercury as an example, we'll have some code in the middle. We're going to initialize the service, add some endpoints, which are just functions, and then run the service. And that's literally it. So when we're adding these endpoints, all we're doing is essentially registering a function that takes a request and returns a response and an error. And this is quite common in Go. Every Go can return multiple return values, and there's a kind of convention that the last return value is an error. This is a particular interface, which lets you get a message out, and you can usually check if it's nil. So what you tend to see in a lot of Go code is a line of code, and then like a line where you check if there was an error, and then another line of code, another line where you check if there's an error, and you're just checking your errors all the time. And the reason for that is you're not throwing exceptions. You can't just let something bubble up the stack. You can panic, which is not the same, and you can recover from a panic, but that's like literally if something has gone catastrophically wrong, and the only reason you'd really recover that is probably to like log the fact that this happened, maybe log a stack trace, and then continue and exit, and then hopefully your binary will be restarted by upstart or supervisor or something. And the reason for that is Go is encouraging you to check your errors at the point that they happen, because that's the only point that you have enough context to decide whether it's something you can, say, retry, or something that you have to immediately abort because, like, memory is corrupted, which Go's memory managed, so you don't get that, but something along those lines, something catastrophic that you cannot deal with. And in our case, we're just registering this endpoint with this function, a name, which is what we're going to do matching on. So if we'll get a request in, we'll match the name, decide which function to execute, and then a request and a response. So in our case, we use protocol buffers. Has anyone used protobuf here? Cool, a few people. And that's really cool, especially in Go, because we can define our interface in one really nice file that is like, this endpoint has this request type and this response type, and it takes these parameters, which are these types. So we can define, it's all statically typed, and these things will be rejected if we don't provide like an integer on this particular field. And by allowing us to register a particular request and response type, all we're doing is, rather than dealing with like unmarshalling JSON and then doing some things and then remarshalling the JSON and returning it back, we can push all of that code out into our library. So we'll get some request in, which in protobuf is binary. Having been given the request type, we can automatically marshal that, so we don't have to do that in our business logic. We're literally like, I have this thing, I will do some code, and then I'll return this particular response type, and then I can deal with my library, will decide whether it was JSON encoded, or binary encoded, or thrift encoded, something like that. So given this function, we've registered a number of things. This particular is like an account service, so we're maybe like dealing with bank accounts. So we could create one, we can read a particular one, we can list them, that kind of thing. And then we're going to run our service. And this will literally start, fire up. We've got a running binary, all good. Which obviously means we need some way to get messages into this. And Go has really good interface support. So in this case, we've defined a server interface. And Go does interfaces a bit like kind of duck typing. So as long as anything satisfies this, it's acceptable as a server, which is cool because you can then have your actual one that does work, and then you can have something that literally just has the same methods, and that can be a mock. So you can do like in-memory testing and make your test suite super fast. And in this case, we will run this server with some form of transport. And again, this transport is an interface. So this transport could be RabbitMQ, where the transport will deal with taking messages off and give us a message and take the responses back. It could be an asynchronous transport, something like NSQ or Kafka, or it could just be HTTP. But as long as it satisfies the transport interface, we can use anything we want, and we could use a different one for each service, which is something we do. And in this case, our transport is going to listen for messages. It does all sorts of other things, but the important thing is it listens with the name of this service, and it will get some requests on like an inbound channel, and it can potentially return an error. So having this interface support is really cool. So if we deploy this in production, this might be like an AMQP interface. But when we're doing tests and we're testing communication between services, this would be like literally an in-memory mock. So like things are going around in like hundreds of nanoseconds rather than milliseconds of latency. And this like request channel here is an example of Go's channel type. So we can literally have a channel that we push requests into, and then there can be any number of things on the other end. So you could have one thread that's just dealing with all the messages, or you could have like a huge number of like a worker pool that allows you to fan these messages out and deal with those. And in our case, actually, we have like a thing on the other end that spins off a Go routine. So we spin off essentially a lightweight thread for every single request. But they're like super lightweight, and the Go scheduler schedules these across multiple cores. It's really cool. Anyway, so with this example, we'd have some API, and we'd send a request to this like subsection of API, and then we send on another request maybe to a service, and then we'll get some response back. And when we do this, we'll send a message through. We need some ideal way of like kind of sending information through these things. So for example, if we've sent a message through this, if we want to like instrument this, we have no way of getting like all of the information here to here unless we pass like everything, including like the request ID, through every single function call. And this could go through any number of things within this binary. But before it gets there, like we need someone to pass this information around. Go does not have things like thread local variables. And you can't do like, well, you could do global state and have like a kind of registry of all requests, but that would be incredibly slow because you're, again, sharing memory. But it does have a really cool context package, which again is an interface. But the cool thing is this part. So we essentially have a blob that we can stick any data into, like this blank interface, like be literally any type, with any key. And we can also pull that back out. And what that means is we can thread this in at one end and then pass it through several layers. And this could be like, this call graph could be 20 services. But we can pass information like the source IP address or like the request ID, something like this, all the way through multiple layers of services. And that allows us to correlate all of the different components. You can imagine like logging in an infrastructure where a request hit 20 services is quite hard. Like you have lots of logs, like so many logs, but like there's about 10 lines in this log file that correspond to my request, and 10 lines here, maybe 500 lines here because something's gone horrendously wrong. But I have no way of correlating those lines together across multiple services, multiple servers, potentially multiple like availability zones. And the only way I can really do that is if I like apply an ID to every request right at the top in the API and have some way of threading that through all of our sub-requests. So with that, we can then pass this through. When we get to this customer API, we have some data about that. We know that this is that 80 whatever request ID. We can do some stuff, we can pass on, we can do some more work, and then come all the way back. So given that we can push like a lot of these things out into additional libraries, things like our dealing with transport, running servers, configuring clients correctly, configuring database clients, we can literally push more and more things into that, and the only thing I have to focus on is the business logic. So I can work like really, really quickly, and I can build stuff really quickly. So in our case, we're doing all sorts of things here. We've got like provisioning your services. I don't really want to know which machines my service runs on. Like, that's not important. What is important is there are a number of them running, and if they fail, they will be like restarted, and everything will carry on working. Things like service discovery. If I need to send a message to the particular service that handles bank accounts, I need that to just get there automatically. I don't want to have to like write lots of code that works out where it is and then sends a request to the right place. Configuration, obviously. Things like monitoring, authentication, authorization. And then also cool stuff like A/B testing. So we could run multiple copies, like different versions of a service, and our client libraries could automatically pick the appropriate one based on some flag or tag that we apply right at the top of the API. This is something actually that Halo do. So when you do a new deployment, you can do like red-blue deployment groups, and you can just deploy a new version, and the message will come in, you can set a percentage of traffic, and it'll go off to perhaps 1, but like you don't have to deploy the entire infrastructure a second time. Like, it'll go to this service and then back to the normal ones, but then maybe back to that group because you've modified that. And again, as long as the interfaces are consistent, that's like super easy to do. And also things like storage and messaging. Like, those should be automatically configured. If I'm writing business logic, I shouldn't be concerned about where my database is, or like the kind of uptime guarantees of that. So a nice way to wrap these up is obviously Docker. So hands up, who's used Docker here? Lots of people. Okay, cool. Now, funnily enough, actually in Go, because you have a single like file, it's actually less useful because you don't need this like consistent environment. But putting stuff in Docker containers means you can like easily deploy them in lots of places because millions of things support them, and you can also get like nice C group support, so you can limit things like CPU usage, memory usage, etc. And it's consistent. It's like a single deployable block that you can put anywhere. But there are a few things that you want to do. Like, if you start off with a Docker container, like, who has ended up with like a 500 mega Docker container? Because you have like all of Ubuntu in there. Like, yes, great. You've got your entire build infrastructure. You've got all these frameworks and everything. And with lots of things, you'll need that because you need like all of the like C-level libraries. You need like the runtime for your language. But in Go, you don't need that because everything's compiled. The whole runtime is statically compiled into the binary. So you can use a Scratch container, which is like 10 meg, which is awesome. And your binary is like 6 meg. So you've got this like super tiny block that you can deploy. However, you do need to actually statically compile it. And turns out Go doesn't quite do that by default. So you have to like tweak some of the compilation flags to make sure that specific super low level libraries are like built in. And a good example of this is SSL usage. So if you just put a binary in a Docker container and put it somewhere, you won't be able to make outbound TLS connections because you don't have the root CA files in your Docker container. So like SSL is now not a thing. But you can just copy those into your Docker container or create one on top of the Scratch thing and just stick that in your build server. And once you have that, you can deploy that anywhere. Obviously, Amazon now have their ECS, the Elastic Container Service. Google have also their container engine, which runs Kubernetes, so you can run Kubernetes on your own hardware, or Mesos, which has a number of schedulers, things like Marathon, Aurora, stuff like that. So in our case, unfortunately, as a bank, you have to run on your own hardware, which is less ideal, because cloud stuff is like clearly the future. And that's kind of just a limitation you have. But if you can put all your stuff in Docker containers, you can ship them anywhere. And you can run like Mesos or Kubernetes on your own hardware. And you can run that on cloud infrastructure. So you can actually like start off, put your testing environments in the cloud infrastructure and your dedicated stuff. And you can move those between super easily. So I mentioned earlier there was like a lot of complexity around this. You've now potentially got 200 services, each of which are running multiple instances in each availability zone. You're running 3 availability zones. You're running on 3 continents, so you've got 3 regions. You've probably got like several thousand binaries running, and you have some way to control this. So the obvious answer is testing. Like literally fire everything you can at these things. Like load testing, failure testing, degradation testing. And failure testing, like Netflix have done a lot of talks about, obviously they have this like simian army, which will terminate random machines, terminate entire availability zones, which they do in production. So that terminates at least 3,000 servers, and they're dead, and they hopefully recover from that. And degradation, where your timeouts are much longer, which usually is worse than something immediately not connecting. And you should be monitoring this as well. So there's a lot of different options. In our case, we allow a function which returns an error. So we can just execute this function, and if it returns an error, we report that into our monitoring infrastructure. But your business logic is the important part, right? So who has acceptance tests? Please, someone put up their hand. Good, lots of people, cool. If you've written those in your application, like, why not run them against your production infrastructure? Like, if you can simulate signing up a customer on your laptop, like, why not also sign up customers in production with the same code? Because then you can assert that those things work. And actually, Halo have an island in the South Pacific that has, like, no population apart from penguins. But there's actually a load of taxis there driving around picking up robot customers. And like that happens continuously. And if that fails, people get woken up. Because fundamentally, like, if you're a bank and someone gets the cash point or their card doesn't work, that's the important part. It doesn't matter if your unit tests pass. If your acceptance tests pass in production, everything's fine. And we can do tracing as well. So I mentioned this earlier. Like, we can take a request ID, we can pass it through, we can instrument, like, sends and receives, both in clients and servers, and then we can aggregate all of that data together. We have an open source tool called Phosphor. There's like Zipkin, Htrace, all the other, like Facebook have their own version, etc. And all this does is takes data from our binaries, sends it through some message bus, and aggregates it in memory. And from that, we can draw like call graphs of a particular call. And I can use my phone, I get a response header which has this ID, and I can look that up. And you can trace asynchronous things as well, which is super important if you're like have an event-driven architecture. And you can draw pretty graphs as well. So this isn't particularly useful, but it looks cool. So like it's great if you have investors coming around. And actually, this is useful in some cases because this red line is like indicating like health failures. So this is like live data that's being read in. It's like volumes of traffic, and then color is like health. So why would we use Go? The language itself is super small. It's very simple, and it's really, really easy to learn. So if you haven't tried it, give it a shot. It's also got amazing concurrency and networking, which if you have like hundreds of applications talking to each other, which are highly concurrent, is quite useful. And the interface support is great because it allows you to like mock out lots of things, use different transports, that kind of stuff. But there are obvious downsides, namely complexity. So you have to invest a lot in like monitoring infrastructure and things like that. And getting started with like microservice architectures is still not a solved problem. So there are lots of tool sets. The Netflix stack's great, it's open source, but you have to buy into that very heavily. You have to like take their entire infrastructure essentially, which is a really huge investment. So being able to break these parts out is super important. And that's about it. So thank you very much. So I'm at Heath on Twitter. GetMondo is Mondo on Twitter. And if you're interested in like joining an alpha, maybe in the next month or two, with like actual cards that give you notifications on your phone before the receipt prints in the machine, then like head over to our website and see more information. Cool.